In the last series of lectures, we had discussed diffusion, the molecular mechanisms of diffusion in liquids and gases. Now, I will go on to dispersion. So far, we have made a distinction between convection and diffusion. Convection is due to the fluid flow, the fluid velocity, and diffusion is due to the molecular velocity fluctuations. Convection is along the direction of fluid flow, it is directional. The molecular velocity fluctuations are isotropic, that is, they fluctuate with equal velocities in all three directions. The average velocity is 0. That means that diffusion takes place only in the direction where there are variations in the densities of the quantities, the mass density, the momentum density, or the energy density. So, the direction of diffusion is the direction of variation of the densities. Okay. And during our discussion, I had drawn a distinction between what were called laminar flows and turbulent flows. Okay. In laminar flows, you have nice straight streamlines. Okay. The fluid velocity is only in one direction and it is steady at any point in time. If you follow the velocity as a function at any position within the pipe, if you follow the velocity as a function of time, the velocity does not change with time. Okay. So, the velocity in this laminar flow as a function of time at some location, okay, the velocity will just have a constant value, okay, and it will be only in one direction, that is the flow direction. Okay. At a Reynolds number of about 2100, there is a spontaneous transition to a flow called a turbulent flow. Okay. The velocity profile is more plug like at the center and it has a greater slope at the wall. In this case, you have fluctuations in all three directions, okay, at any point. Okay. Fluid, there is fluid motion in both the streamwise and the cross stream directions in the form of what are called fluid eddies, which are parcels of fluid in correlated motion. Okay. So, if I plot as a function of time, okay, if I plot, for example, if I consider this as the x direction and the two perpendicular directions as y and z, okay, the velocity along the flow direction at a particular point in time, okay, it will fluctuate about a constant value. Okay. If I do the time average of this Vx, it will be a constant, but instantaneously it will be fluctuating, there will be time variations. Similarly, there will be time variations in the other components as well, okay, at that same location. Okay. So, there will be time variations in both Vy and in Vz. Since the flow is on average in the x directions, the average of the velocities in the other two directions have to be 0. But however, instantaneously they will not be 0, because there are eddies whose velocities are in all three directions. Of course, as you come very close to the wall, the no slip condition has to apply, therefore, all velocities have to decrease to 0. But within the bulk of the flow at any location, there will be fluctuations in position and in time in all three directions. Okay. So, in order to describe this system, what is usually done is to express the velocity as the function as the sum of a mean and a fluctuating part. Okay. So, if I take a time average a time period t average, okay, which is large compared to the time scale of the local fluctuations, okay, which is large compared to this time scale, I can define an average velocity, okay, V x bar, okay, is equal to 1 over the averaging time integral 0 to averaging time dt times V x. that is the average velocity at this location in the x direction. Okay, that is the average velocity at this location in the x direction. So, this is V x bar. Okay. And similarly, you can define the other two components of the velocity, okay, V y bar and V z bar. Okay. So, okay. So, this is the mean velocity at a particular location, okay, in the flow. Okay. So, that is the mean velocity, and I can also define a fluctuating velocity. Note that V y and V z both have to be equal to 0, because there is no flow on average in the y and z directions, the cross stream directions. Okay. There is no flow on average in those two cross stream directions. In the x direction, there is an average flow. Okay. Now, once I have this definition of the average velocities, I can define the fluctuating parts. Okay. V x prime is equal to V x minus V x bar, where V x is the instantaneous velocity and V x bar is the average velocity. So, these excursions from this average velocity, okay, these excursions from this average velocity are basically V x prime, the fluctuating velocity, and V x prime satisfies the condition that 1 over the average of this has to be 0. Okay. You can get this by taking the average of this entire equation, because the average of V x is equal to V x bar and V x bar is independent of time. Therefore, the average of V x prime has to be equal to 0. Okay. In this particular case, V y prime is equal to V y bar and V z prime is equal to V z bar. Okay. So, therefore, in summary, I have expressed V x is equal to V x bar plus V x prime. V x bar is equal to 1 over the averaging time long compared to the time for the fluctuations in the velocity. Okay. Averaging time long compared to the time for fluctuations in the velocity. This flow is statistically steady. If you average over time, you get the same answer for the velocity profile. Instantaneously, there are fluctuations. Okay. So, when you average over that, you get V x bar, okay, and the average of V x prime, okay, is equal to 0. Okay. And similarly for V y and V z. Okay. Now, transport in a turbulent flow. Okay. Transport in a turbulent flow. Okay. I have fluid velocity fluctuations, and these parcels of fluid in correlated motion will carry along with them the concentration from the initial location to the final location. Okay. These parcels of fluid in correlated motion will carry with them the concentration from the initial location to the final location. Okay. So, because of this velocity fluctuations, there will also be fluctuations in the concentration field or the temperature field. Okay. We will consider the concentration field first. Okay. So, therefore, the concentration field I can also write it as C bar. Okay. If I plot the concentration field as a function of time, okay, at a location, because this concentration, this mass is being transported by these turbulent eddies, okay, because this mass is being transported by these turbulent eddies, there will be of course a average concentration, but about that there will also be fluctuations in the concentration. Okay. There will be an average concentration plus fluctuations about that average concentration. Okay. So, therefore, C can also be written as C bar plus C prime. okay, where the average concentration is defined in a similar manner. Okay. And the average of the fluctuating part is equal to 0. Okay. And you can do a similar thing for the temperature. It is exactly analogous, so I will not go through that. Okay. So, what is the flux? Okay. You recall that we had discussed the flux across a surface, okay, as, okay, a parcel of fluid which, okay, okay, which moves across a surface with the normal velocity v n, and it, okay, and after a time delta t, this parcel will go to the other side of the surface. Okay. Okay. And we had calculated the transport across the surface as the surface area delta S, okay, delta S times V n times the concentration, okay, times delta t. That was the transport within a time delta t, okay, this is equal to transport in delta t, and therefore, the flux is equal to this transport by delta S delta t, which is just equal to the concentration times V n. Okay. Kindly refer back to the lectures on convection and diffusion earlier. The expression for the flux is C times V n. Okay. So, for example, the transport in the x direction, okay, in the x direction, the flux J x at a particular location is going to be equal to V x times C. Now, we had separated out the velocity into the average, the mean and the fluctuating parts, and we had also separated out the concentration into the mean and the fluctuating parts. We can also write down the flux as the sum of a mean and a fluctuating part. Okay. The average flux, the time average flux is equal to 1 over T average integral 0 to T dt times the instantaneous flux J x. Okay. That will be the expression for the average flux. Okay. So, let us expand this out and see. Okay. J average this is concentration times V x is the flux in the x direction. I can write this as 1 over T average integral 0 to T average C bar plus C prime into V x bar plus V x prime, expressing it as the sum of a mean and a fluctuating part. Okay. So, therefore, this average flux, okay, is equal to, I can expand this out, just expanding out this product here, okay, just expanding out this product here. Note that Vx bar and C bar have already been averaged over time, okay. These are already averages. So, they are independent of time, okay. Vx bar and C bar are independent of time, okay. Vx prime and C prime do depend upon time, okay. So, therefore, this first term is just equal to C bar Vx bar because it is independent of time. Okay. The second term C bar is independent of time. Okay. So, I get C bar by T average. The third term Vx bar is independent of time. And in the fourth term, both of them are dependent on time, so I cannot take it out. Okay. The first term, the integral is just T average, so I just get C bar Vx bar. Okay. Second term, average of Vx prime is 0. So, this average is equal to 0. Okay. Third term, the average of C prime is equal to 0. All primed quantities average to 0. Okay. However, the fourth term is not 0 in general. Okay. The fourth term is not 0 in general. This term is 1 over T average, integral 0 to T average dt of Vx prime C prime. Okay. Alternatively, this can be written as C bar Vx bar plus C prime Vx prime the whole bar. Okay. Note that the first term is the product of two averages. Okay. C bar times Vx bar is the product of two averages, the average concentration times the average velocity. C prime Vx prime is the average of the product. Multiply C prime and Vx prime and then take the average of both of them. Okay. So, that is the second term. Okay. So, therefore, the mean flux, it has one component of course due to the mean flow. Okay. It has one component of course due to the mean flow, okay, plus a second component which is the average of C prime and Vx prime. Okay. The first term is flux due to the mean velocity, okay, and the second term is what is called turbulent dispersion, okay, the product of two fluctuation quantities averaged over time. Okay. And this term is in general non-zero. Okay. This term is in general non-zero. Okay. This is what is called the Reynolds flux, okay, J x Reynolds, okay, is equal to the average of C prime Vx prime in the x direction. I could do the same calculation in the y direction and I will get C prime Vy prime. In the z direction I will get C prime Vz prime. Okay. Now, this product is in general non-zero. Okay. The reason is because if I have a quantity, okay, let us say I just take Vx prime, okay, as a function of t, okay, it averages out to 0. Okay. If I take for example Vx prime square and then I average, okay, Vx prime square is necessarily positive, it is the square of a number. So, even though Vx prime goes between positive and negative, Vx prime square is always negative and therefore, its integral has to be, I am sorry, Vx prime square is always positive and therefore, its integral has to be positive. Okay. Similarly, if I have two quantities, okay, if I have two quantities Vx prime and C prime, okay, even though individually, okay, Vx prime C prime versus t, Okay. Even though individually both quantities may have a 0 average, okay, even though individually integral dt Vx prime is equal to 0, okay, the product of these two does not necessarily have to be equal to 0. Does not have to be 0. Okay. If C prime is positive more often when Vx prime is positive, this will be positive. If C prime is more often negative when Vx prime is positive, this will be negative. Okay. So, when there are correlations in the fluctuations of these two quantities, okay, correlations in the fluctuations of Vx prime and C prime, the product of these two does not necessarily have to be equal to 0. Okay. And this is what results in dispersion, turbulent dispersion. The fact that there is a correlation between the fluctuations in the velocity and the concentration field results in a net average flux. The concentration fluctuations and the velocity fluctuations on average are 0. The product of those two are not necessarily 0 because they are correlated, and that results in a net flux. And that flux is the flux due to turbulent dispersion. It is also called the Reynolds flux. The same thing for heat transfer is the thermal Reynolds flux. For momentum transfer, it is the momentum, the Reynolds stress or the Reynolds momentum flux. Okay. So, I will give you an example of how fluctuations could be correlated. Okay. The concentration and velocity at a point are C prime is equal to C naught prime sine of omega t. Okay. Vx prime is equal to Vx naught prime into sine of omega t plus phi. Okay. So, therefore, the concentration field C prime, okay, so has a sinusoidal form. Okay. As a function of time. Okay. The velocity field Vx prime has some other sinusoidal form. Okay. It has some other sinusoidal form. Both of these average to 0. Okay. The average of the concentration fluctuations is C prime average is equal to 1 over T average integral 0 to T average dt sine of omega t, okay, times C naught prime. Okay. I just take an integral of the sine omega t is minus cos omega t by omega. Okay, that is all I have substituted. Okay. Okay. So, this will be equal to C naught into 1 minus cos of omega t average by omega t average. Okay. So, you can easily verify, okay, if T average is much larger than the characteristic time of these fluctuations. The characteristic time of these fluctuations in this case is 2 pi by omega. Okay. The characteristic time of these fluctuations is 2 pi by omega. Okay. So, if T average much greater than 2 pi by omega, which means that omega t average much greater than 2 pi. Okay. 2 pi by omega is the period of the fluctuation in the concentration, and therefore, t average has to be much larger than 2 pi by omega, much larger than the period of these oscillations. Okay. In this particular case, this will be the period. Okay. Okay. If it is much larger than this, then you can see the numerator 1 minus cos omega t, this is, it has to be between 0 or minus 1 and plus 1. Okay. Because cos omega t varies between minus 1 and plus 1, I take 1 minus that. Okay. Numerator is finite, the denominator is large, and therefore, this c prime is approximate tends to 0 when omega t average is much greater than 2 pi. Okay. So c prime on average tends to 0. Okay. Similarly, Vx prime average also tends to 0. Into Vx naught prime. Okay. Is equal to minus Vx naught prime by t average omega into 1 minus sorry. In this case as well, cos omega t is bounded and t average omega tends to infinity when t average is much larger than 2 pi by omega. Okay. The numerator becomes large when the averaging time becomes large. The denominator becomes large when the averaging time becomes large. The numerator is finite, it is bounded, okay, it is a cos function. So, therefore, this also goes to is equal to 0. If I take the average of the product, for example, Vx prime C prime the whole average, okay, is equal to 1 over t average integral 0 to t average, okay, into C naught prime sine of omega t, Vx naught prime sine of omega t plus phi. Now, I have to use the relation, okay, the identity sine of omega t sine of omega t plus phi the trigonometric identity. Okay. This is equal to sine of omega t into sine omega t cos phi plus cos of omega t sin phi. Okay. And I can do one more in order to I have sin square omega t and sin omega t cos omega t here. Okay. So, I have these two products. Okay. I can use trigonometric identity once again to simplify these, okay, and I will get half of one minus cos of 2 omega t cos phi, okay, plus sine of 2 omega t sin phi. Okay. Sin square omega t is half of 1 minus cos 2 omega t, sin times cos is half of sin 2 omega t. Okay. So, that is why I have this factor here of a half. Okay. Okay. Kindly revise your trigonometric identities if you are not familiar with this. Okay. So, I substitute this, okay. Vx prime C prime average is equal to 1 over t average integral 0 to t. Okay. I can take the constants out. Okay. Half of 1 minus cos of cos phi plus and I can carry out the integral. Okay. I will take the factor of 2 outside. When you do the integral, you will get a t minus sine of 2 omega t by 2 omega. And T average. Just carrying out the integrals. Okay. You can see that the T average in the first term cancels out with that in the denominator. Okay. So, I get C naught V x naught prime into T average will cancel out, I will get cos phi by 2. Okay. Okay. The other terms have an omega T average in the denominator, okay, have an omega T average in the denominator. In the limit as omega T average goes to infinity, when T average is much larger than 2 pi by omega, these terms all go to 0, okay, just as we got the averages. Okay. So, therefore, C prime V x prime average is non-zero, even though the average of C prime and the average of V x prime are both 0. That is because the fluctuations are correlated. Okay. In this particular case, C prime is positive more often when V x prime is positive and vice versa. Okay. And because of this correlation in the fluctuations, we get a positive value for the flux due to fluctuations, even though the individual fluctuations themselves average to 0. Okay. So, this is the mechanism of dispersion. Correlation between fluctuations in the density of the quantity, mass, momentum and energy, and the velocity will result in a non-zero contribution to the time average flux, even though the individual fluctuations are all 0 on average. So, I will continue this discussion on dispersion a little more in the next lecture, and then we will look at dispersion in packed columns and dispersion, Taylor dispersion in a pipe. I will continue this in the next lecture. I will see you then.